Hello Demuxed. My name is Hadi Amirpour from the Athena team University of Klagenfurt, and I'm going to be talking about per-title encoding for live video workflows. First, I will give a brief introduction about per-title encoding and its challenges. Then I will introduce our open source software Video Complexity Analyzer or VCA, and at the end I will present how we use the features extracted by VCA to improve per-title encoding for live streaming. We know that videos show different rate distortion behaviors. Here, as an example, we show rate distortion performance of two different videos encoded at the same bitrate resolution pairs, and we can see there is a huge difference between their behaviors. In the first video, it is 1080p that outperforms other resolutions, almost in the whole bitrate range except in the very low bitrate. Therefore, convex hull is mainly made of 1080p resolution for this video. But for the second video, we can see that there are crossover bitrates and the optimal resolution varies according to the encoded bitrate. With the increasing bitrate, the optimal resolution is also increasing from 270p to 720p, but interestingly, 1080p is not selected for the given bitrate range. Therefore, convex hull is made of various resolutions, and the comparison with the previous convex hull shows its content dependency. So we need to encode the same video at multiple bitrate resolution pairs to find the convex hull. But it will be not only very expensive to use this brute force approach, but also it's not applicable in live video streaming due to the additional latency that is introduced by the brute force approach. So we need to predict the convex hull. If we could predict the convex hull real time for live video streaming, the second challenge will be selecting the best representations from the predicted convex hull to construct the optimized bitrate ladder. These challenges motivated us to find the solutions for online per-title encoding in live video streaming. To this end, we need to extract some features from the video which can aid the encoding process and help us to answer some questions, such as where to encode, what bitrate ladders to select, and what encoding parameters to set. The state-of-the-art spatial and temporal complexity feature is SITI, but the time taken to compute SITI features is very high, and the correlation with encoding bitrate and encoding time is very low. So what is the solution? To solve these problems, we introduce Video Complexity Analyzer or VCA that can be realized as a fast preprocessor, which determines the spatial and temporal complexity of videos or video segments to aid the encoding process. To extract the spatial complexity for frame number P, we divide it into smaller non-overlapping blocks of size W cross W, and for the block number K, we introduce energy function or H as the weighted DCT value. So for each block, we first calculate its DCT and then we introduce H as the weighted DCT values. By averaging over entire blocks of a frame, a spatial complexity for that frame is obtained. To calculate temporal complexity for frame P, we consider frame P itself and its previous frame, and we calculate the energy function for two collocated blocks in both frames. And then we calculate SAD between the energy functions. By averaging over entire blocks, temporal complexity feature for frame P is also extracted. Here, heat maps of spatial and temporal complexity features for the same video content are shown. DCT calculation is quite fast, and by CMD optimization and multi-threading, we can reach around 400 frames per second feature extraction, which means that these features can be used in live video streaming without adding noticeable latency. To evaluate the accuracy of these features, we encode 500 videos in all intra mode and consider their bit rates as ground truth labels for spatial complexity. It is seen that our spatial complexity feature E shows higher accuracy compared to the SI spatial complexity feature. We also encode all of these 500 videos in low delay intercoding mode and calculate the correlation between spatial and temporal features with encoding bitrate. Again, our proposed features show higher accuracy. We also calculate the correlation between features across multiple resolutions, and we can see that the proposed spatial complexity feature has better correlation across different resolutions. Considering the feature extraction speed and the accuracy of features to represent complexity of a video, we use these features to predict the convex hull for a given bitrate range and optimizing the bitrate ladder. Here you can see the workflow for our online per title encoding approach. When a video segment is captured, its complexity is analyzed and then an adjusted encoding profile or an adjusted bitrate ladder is constructed. This will allow us to have optimized bitrate ladders for different content types. For example, for a middle complex, simple, and complex videos, we may have different bitrate ladders. As an example, we encode the same video at 1.6 megabit per second, first by the resolution recommended by HLS ladder, that is 540p, and second with the resolution predicted by our online per title encoding approach, that is 1080p. Here we can see that 1080p, which has been predicted by our online per title encoding approach, shows better quality than the HLS ladder. We tried our approach on various video segments, and on average we achieve around 30% bitrate saving using VMAF as the objective metric and 20% bitrate savings using PSNR as the objective quality metric. So when we could predict the convex hull, the next question is that which representations should be selected from the convex hull to construct the bitrate ladder? There are many cases that selected representations show very similar qualities. As you can see on the y-axis, the selected representations have similar VMAFs in higher bit rates, and the difference between these qualities are not noticeable actually. We propose perceptually aware per title encoding approach that select representations from the convex hull in a way that there is one just noticeable difference, or JND, between two adjacent representations. In this way, we guarantee that there is no two adjacent representations, that the difference between their quality is not noticeable. And in this way, we can reduce the number of representations in our bitrate ladder and consequently reduce the CDN and streaming costs. Here you can see that the perceptually aware per title encoding approach compared to HLS ladder can achieve around 30% bitrate savings using VMAF as the objective metric, 15% bitrate saving using PSNR as the objective metrics, and around 30% CDN or streaming cost reduction. Our open source software is available at the following links. And at the end, I would like to thank my colleagues, Vignesh from Athena, who was the main contributor of VCA, Christian Fidman from Bitmovin, who optimized the software, and Christian Timmerer. Thank you very much for your listening.